Welcome to section 5.1, Proving Identities. So before we get into proving identities, let's quickly review three essential families of trigonometric identities. The three essential families are the reciprocal identities, the ratio or quotient identities, and the Pythagorean identities. These are fundamental tools that help us simplify and manipulate trig expressions. The reciprocal identities express the trig functions as the reciprocal of another function and the reverse. So cosecant theta is equal to 1 over sine theta. Sine theta would be 1 over cosecant theta. And then the other trig functions and their inverses, secant and cosine and cotangent and tangent. These are especially helpful when you're given one trig function and need to find its reciprocal. Ratio identities express tangent and cotangent in terms of sine and cosine. So the tangent theta equals sine theta over cosine theta. Cotangent, which is the reverse of tangent, would be cosine theta over sine theta. And these are commonly used when simplifying expressions or when converting everything to sine and cosine. The Pythagorean identities are based on the Pythagorean theorem and describe the fundamental relationship between trig functions. So the Pythagorean identity, cosine squared theta plus sine squared theta equals 1, gives us the following trigonometric identities here on the right side. So all of these are derived from this first Pythagorean identity. Okay. The other Pythagorean identities we have are 1 plus tan squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. These identities are incredibly versatile, especially for solving equations and simplifying complex expressions. So in section 5.1, we have one learning objective: prove trigonometric identities. So we're going to use those three essential families of trigonometric identities in order to prove the following identities. So when you're asked to prove a trigonometric identity, your goal is to show that two expressions are equivalent by using algebraic steps and known identities. Think of it like a puzzle. You're transforming one side of the equation until it matches the other. It's important to remember you are not solving for a variable, you are verifying that the two sides are always equal. So here are some guidelines for proving trigonometric identities, and I have 5 of them. So to make your work clear and successful, we're going to follow these helpful strategies. Step number 1, you're going to start with the more complicated side. So this is going to be the side that probably has the most trigonometric identities shown. This gives you more to work with and usually more options for simplification. 2, use trigonometric substitutions. So you'll apply the reciprocal, the ratio, and the Pythagorean identities in order to rewrite parts of the expression so that you can simplify it down to the expression you would like. 3, apply algebraic techniques. So just because it's trig does not mean that we have to forget what we know, like algebra. We can use our factor formulas, we can distribute, we can combine fractions to simplify the expressions by creating common denominators with the same name. All that we know about algebra, we can still utilize in trying to prove trigonometric identities. 4, convert to sines and cosines. So if you're stuck, rewriting everything in terms of sine and cosine often helps in simplifying things. When it's written in sine and cosine, you're able to identify other trigonometric identities that you know in order to simplify your expression to what you'd like. And then number 5, keep an eye on the goal. All right, so always compare your progress to the side you're trying to match as you go along. Am I getting close? What am I missing? Is it similar? Can I just rewrite it with a reverse? always keep in mind what you're trying to get your expression to look like. So there's a natural flow to proofs, and staying focused on your goal helps guide your steps. Okay, so now that we have these guidelines, these strategies, let's now prove the following equations. The first one that we're going to prove is tan theta divided by secant theta equals sine theta. So I am going to work with the left side because this is the more complicated side versus the right side. So I'm going to start off with tan theta over secant theta. Okay. Now this ratio is written as a fraction. I'm going to write it horizontally as tan theta divided by secant theta in order to allow me to see the operations that I'm going to be utilizing. So writing it as a fraction is very similar to writing it horizontally here using the division symbol. So I know tan theta is the sine theta over cosine theta. And I know secant theta is 1 over cosine theta. Remember, my goal is to get this expression to look like sine theta. So I need to incorporate sine theta somewhere in this problem. And I know tangent can be rewritten with sine. Okay, so now that I have rewritten my tan theta and my secant theta, I now am going to apply the division symbol, which means I can convert this to a multiplication problem by flipping the second ratio, so taking the reciprocal, and I change the operation, also known as keep, change, flip. So now that I have applied that, I can see here that my cosines cancel, leaving me with just sine theta, which is the expression that I'm trying to simplify to. Okay? And so I was able to prove that's tan theta divided by secant theta equals sine theta. All right, number 2, prove cotangent x plus 1 equals cosine x times cosecant x plus secant x. Okay. All right, so the more complicated side here is the right side, and so that's the side that I'm going to work with. So let's rewrite that. Cosine x times cosecant x plus secant x. And I need it to look like cotangent x plus 1. Okay? All right. So first thing that I'm going to do is I'm going to rewrite what's in my parentheses in terms of sine and cosine. So cosecant is 1 over sine, and secant is 1 over cosine. Okay. Now I'm going to distribute the cosine to each term. So that'll be cosine x over sine x plus cosine x over cosine x. Now I can simplify this. So cosine x over sine x is cotangent x, and cosine x over cosine x is 1, which is the expression I'm trying to prove. Okay, awesome. Let's do another one. Prove cosecant squared x minus 1 divided by cosecant squared x minus cosecant x equals 1 plus sine x. So we're going to start with the more complicated side. Okay. So we have cosecant squared x minus 1 in the numerator and cosecant over cosecant squared x minus cosecant squared x. Okay, so we're going to expand this ratio using some algebraic formulas. So in the numerator, we have two perfect squares that are being subtracted from each other. So that's the difference of squares, because cosecant x is being squared and 1 is a perfect square. So I can rewrite this as cosecant x minus 1 times cosecant x plus 1. Okay. And that's going to be divided by, okay, in the denominator, I have two terms where I can factor out a cosecant x. So that will give me cosecant x minus 1 in parentheses. So again, I'm trying to get this to look like 1 plus sine x. So let's now simplify this ratio. I have cosecant x minus 1 in the numerator and denominator. So simplifying this gets me cosecant x plus 1 over cosecant x. Now let's split this ratio into two fractions. So cosecant x over cosecant x plus 1 over cosecant x. Well, cosecant x divided by cosecant x is 1, and 1 over cosecant x is equivalent to sine x. So 1 plus sine x is equivalent to this trigonometric ratio. Ooh, that was fun. Okay, so now we're asked to prove 1 minus cosine theta equals sine squared theta divided by 1 plus cosine theta. So more complicated side is the right side. So I'm going to work with sine squared theta over 1 plus cosine theta. Okay. All right, so I want it to look like 1 minus cosine theta. 1 minus cosine theta. Okay, so that's very similar to one of the Pythagorean identities. Okay, so let's rewrite our numerator as 1 minus cosine theta, because we don't want any signs in our expression, because that's what we're trying to get. So I need to rewrite sine as in terms of cosine. So I'm going to rewrite sine squared theta as 1 minus cosine squared theta, which is one of the Pythagorean identities. Then I see here that my numerator is also a difference of perfect squares. So a difference of squares. 1 is a square and cosine squared is a square. So I can rewrite this as 1 minus cosine theta times 1 plus cosine theta all over 1 plus cosine theta. So I have 1 plus cosine theta in the numerator and denominator, which cancel out, leaving me with 1 minus cosine theta, which is exactly what I'm trying to prove. Alrighty. Prove sine theta times cosine theta equals sine theta minus cosine theta divided by secant theta minus cosecant theta. All right, so this is the more complicated side. So that's what we're going to be working with. So sine theta minus cosine theta divided by secant theta minus cosecant theta. And I want it to be equivalent to sine theta cosine theta. Okay, so because I have two trig functions that I'm subtracting in the numerator and denominator, I'm going to rewrite this as a horizontal division problem. So I have sine theta minus cosine theta divided by secant theta minus cosecant theta. Okay. All right. So the secant theta and the cosecant theta, Since I want it only in terms of sine and cosine, I need to rewrite secant and cosecant in terms of sine and cosine. So I can rewrite this as 1 over the cosine theta minus 1 over the sine theta. Now I want same denominators. I want them to have the same name. So I'm going to be multiplying my first ratio by sine theta in the numerator and in the denominator. And then 1 over sine theta, I'm going to multiply by cosine in the numerator and in the denominator. In doing that, I will then have the same denominator, which will be cosine theta sine theta. Then in the numerator, I'll have sine theta minus cosine theta. Okay? So that will be the same. And then I still have my sine theta minus cosine theta over here on the left. That has not changed. Okay? So now let's apply that division symbol. So we have sine theta minus cosine theta times the reciprocal cosine theta times sine theta over sine theta minus cosine theta. The numerator in our first ratio is the same as the denominator in our second ratio, so those cancel, leaving us with cosine theta sine theta, which is equivalent to what we're trying to prove. All right, prove 1 over 1 minus sine x plus 1 minus sine x over cosine squared x equals 2 secant squared x. So I don't know about you, but that left side looks a little bit complicated. So that's exactly what we're going to be working with. So 1 minus sine x, so 1 over 1 minus sine x plus 1 minus sine x over cosine squared x. Okay. All right, so we want it to look like 2 secant squared x. Secant squared x. All right, so what can we do here? Well, we know that we only want one trig function, which means that we have to combine these two fractions together. So we need common denominators so that we can combine them into one term. So how can we do this? And there's many ways that we can approach this. For this problem, what I am going to do is I want to get cosine squared x as my denominator. So I am going to multiply the numerator and the denominator by 1 plus sine squared. Actually, no, 1 plus sine x. Let's get that sine x. 1 plus sine x. Okay. And in doing so, that will get me 1 plus sine x divided by 1 minus sine x times 1 plus sine x, which is written in the formula of the difference of squares. So I can rewrite that as the difference of two squares, which would be 1 plus, sorry, not plus, difference, 1 minus, my apologies, 1 minus sine squared x, and then my second ratio is still the same. Okay, now 1 minus sine squared x is equivalent to cosine squared x. So now my denominators have the same name, cosine squared x. Since they have the same name, I can combine their numerators. Okay, so I'll have 2, and then the sine x and the negative sine x cancel over cosine squared x. Okay, well, I know that 1 over cosine is secant, so 1 over cosecant squared would be secant squared x. So 1 over cosine squared x, sorry, will be the same as secant squared x, which is what we're trying to prove. All right. Okay, now we're trying to prove 1 plus cosine t over sine t equals sine t over 1 minus cosine t. Okay, so in looking at this, both sides seem complicated enough. So it doesn't matter which side you choose, you will be able to get from one to the other because they're very similar in complications. So we're going to choose the left side. I challenge you to do the right side and see if you can get to the left side. Okay. All right, so I want sine t over 1 minus cosine t. So I'm going to multiply the numerator and denominator by 1 minus cosine t. 1 minus cosine t. All right. In doing so, I will then get 1 minus cosine squared t in the numerator, because that would be the difference of squares. And then I would have sine t times 1 minus cosine t. Okay. Next, the numerator 1 minus cosine squared t is a Pythagorean identity. So that's equivalent to sine squared t. The denominator I'm going to keep as 2 factors. Now, because I have 2 signs in the numerator, I can cancel out the sign in the denominator, leaving me with sine t over 1 minus cosine t, which is the trig identity we're trying to prove, is equivalent to 1 plus cosine t over sine t.